It's beginning to look a lot like statistics. Every school you go, take a look, oh, it's 12:10.
Oh, man.
Alright, so let's go over absolute versus local extrema. Absolute extrema, you must look at the graph as a whole and find the highest maximum and the lowest points. Lowest would be called the minimum. Local extrema, another word for local, you can write relative. Another word for absolute, you can write global. Relative extrema, the word extrema just basically means max or mins, just fancy words. You localize what you look at when you look at the turning points. Let me go ahead and draw you guys a quick example. Say this is my so this would be considered a turning point. We've learned the words increasing and then it switches to decreasing. So that would be a turning point. TP, turning point. Turning point. Turning point. So maximums occur at peaks. So in this case, we have a maximum. And you'll notice that in our graph, this one is actually considered both a absolute maximum, and you can also consider it a local maximum. I'll explain that in a second. Local extrema cannot occur at the endpoints, so these are the endpoints. With all extrema, you must list the y-coordinates as your value for the max or minimum. Now, why did I consider this the local maximum and the absolute? Well, this arrow tells you that the graph keeps going down, so this is already the highest point of the graph. And it might be, you know, I took my son to the mountains. Let's just say we lived in Nepal. In our backyard, Mount Everest could be local to us. Does that make sense? It could be a 1-minute drive to get to Mount Everest, and you just look straight up. Okay, so in this case, this is both a local maximum and an absolute maximum. Now, this order pair here is 1, 1. So abbreviations, you might write something like this. The absolute maximum, what we just read here is it says the y-coordinates. So if you circle the y here, color, we would just write an absolute maximum equals to 1. You're looking at the y values. You're just looking at how high it goes. You can also write down the order pair. And that's our definitions of absolute, local, minimum, and maximums. Alright, this graph does not have an absolute maximum point. The reason why it doesn't have an absolute maximum point, because the graph continues on to positive infinity. How do I know it goes to positive infinity? Well, I see these arrows. And so the graph keeps going up. So there's going to be some really high point that we can't even see on our graph. Okay? So pay attention to the end behavior. In this case, it has arrows for what we know right now. This example here, this graph does have an absolute maximum and a minimum because the graph stops at the endpoints. You guys see these endpoints? This means the graph does not continue on forever. So the bottom endpoint is the absolute minimum. And the top is the absolute maximum. So let's practice writing that last one here. Class, what's the order pair here? 3, 3. And which one is the y-coordinate? So we can say an absolute maximum at 3. That's how we would write it. So use the order pair. It is a hint. Circle the y-coordinate and you put equals to 3 or at 3. Alright, so today's lesson was talking about our 3 types of how would you describe a function. What does it mean to be increasing? Increasing on an interval. So think of it kind of like a TV show. You start, Jeopardy starts at 7 and ends at 7:30, right? It's a segment, it's an interval, starts and ends. If any 2 points in the interval, a positive change in the x, so positive change in the x is going which direction? How do we get positive x value? This way or this way? Left to right. So what it's saying is you go from left to right. What happens in a positive change in the f of x values? Look at this green box. We had just said that this was increasing. So the formal definition is from this point to this point, you can basically do slope. Does that make sense? And you'll have a positive. If it's decreasing, you go from left to right. And then the change from this to here, if you do slope again, you'll find that it's a negative. It's just going down. The values in y are changing. And then something we don't have is a constant. A constant would look like, let's say I want to change this graph. People have surgeries because they're not happy with themselves. That would be a constant. You see it? From this point to this point, your slope is 0. So that would be an example of a constant. So increasing, decreasing, and constant. Alright, so we have a graph here. It asks us 3 questions about the graph. How many turning points does this function have? How many real zeros does it have? And what appears to be the degree of this function? So my kids don't like it. You're driving. And then they notice something. They kind of stop, right? Hey, Dad, how come you're making a U-turn? Made a mistake, kids. I made a wrong turn, right? Missed the exit. So here, this is called a turning point. Everyone say turning point. It's a turning point because you're going from increasing to decreasing, right? Maybe you're kind of sad about this class, right? Your grades, maybe. And you realize, you know what? I'm going to go to college. I'm going to make something of myself, right? You have a turning point in your life, right? You start increasing and thinking positively about life, right? So that's what a turning point is. So, question number 1. How many turning points does this function have? Let's count. Ready, set, go. 1, 2. So we have 2 turning points. Next question asks, how many real zeros does it have? Zeros refers to the x-intercept. Reals means that it touches or crosses through. Let's count. Ready, set, go. So we have 3 real zeros. Now they ask us a question. What appears to be the degree of the function? Well, I noticed the end behavior. One starts down, one starts up. Well, what really easy equation does that? A linear equation. Y equals x to the first power. This degree here is odd. Starts down, ends up. That matches ours, so ours has to be an odd degree. And the answer for this problem is 3. So to review, the degree of our function is equal to the, at most, maximum number of x-intercepts. They call this fancy word the fundamental theorem. Fundamental theorem of algebra. And then the second idea we just learned from here is that the number of turning points, class, what does that stand for? Is going to be your degree minus 1. So the most amount of turning points we'll have is your degree. In this case, it is a 3. So 3 minus 1 gives us the 2. Alright, anyone see any observations? David? What about the end behavior? Yes? Good. So he recognizes that the odd degrees start down and up as our end behavior. Yes. You can also apply that to the 2s and the 4s. The even degree polynomials, it starts up and also ends up in the same direction. Okay? I did want you guys to focus on the x-intercepts. Here in yellow. Anyone see anything? Anybody? What happens at the odd degrees? It goes through the x-axis. How about the evens? It bounces or touches, or we'll talk about that it actually kisses the x-intercept. Okay? So let's write some steps here. Steps to graphing polynomials by x-intercepts. So ask yourself a question, is it factored? The next question, can you get a basic graph? Number 3, what's its multiplicity? Oops. Today we'll learn about the zero product rule. ZPR. We'll also learn about how even degrees, they kiss, and that odd degree functions, they will do something called a shoot through. Shoot through. And then to finish that off, we should ask some questions. Number 4, are there any transformations? You're copying this down. Or shifts. And then lastly, you're going to graph it. So here are my steps to graphing polynomials by x-intercepts. Here's an example of an odd degree. If it has an odd degree, you're going to do, they call this the multiplicity. Everyone say multiplicity. It's just a fancy word of saying their degree. And in this case, it is an odd, so you're going to shoot through. Evens are like this example here, x to the 4th. It's going to kiss or bounce off or touch the x-axis and then run away.
On the 12th day of math, Miss Mr. gave to me 12 packets scanning, 11 discriminants, 10 parabolas, 9 x boxes, 8 times table, 7 vertex form, 6 y-intercept, 5 expressions, 4 fx functions, 3 practice tests, 2 wag forms, and the axis of symmetry.